Okay, here are the notes on piecewise functions. To start off, you'll definitely need some graph paper. And as we go along, you'll want to pause this video to copy down the graphs as precisely as possible. To start off, let's talk a little bit about notation. Piecewise functions kind of follow this similar notation where I have f of x is equal to, I have this fancy bracket on the left, and then some rule followed by a domain. Now, I've got 3 written here in a row. It could be 2, it could be 4, it could be as many as possible, as long as it's more than 1. The rule is just an equation. Could be a linear equation, a quadratic equation, a absolute value, any type of equation. And then the domain for our uses today, we're going to write this in inequality form. So we're going to use like less than, greater than or equal to, and other similar symbols. Today, we are going to focus only on linear pieces. So think about slope-intercept form, y equals mx plus b, and f of x equals mx plus b. All right, those are the same thing. Y is the same as f of x. So example 1, write the piecewise function for the graph and identify the domain and range. If you need to pause here to copy more down, that's great. I'm going to zoom in on this graph so that you can see it really carefully. And you may want to pause again to get that graph down as perfectly as possible, making sure you're hitting all the right points. Keep in mind I've got different colors going on here, which might be helpful to use for your first graph. Some open circles versus some closed circles. Start off with the first graph, which is this one all the way on the left, this red one. And I'm going to color coordinate my equations here. So this very first part of a line, things to notice. My first dot here is closed. So we'll talk about what that means. My dot up here at the top is open. So that's going to change things for my domain. And I'm going to write the equation of this line. To write the equation of the line, I need the y-intercept and the slope. Well, the y-intercept right here is just at -4. And the slope, I'm just going to count the rise over the run between any 2 points. So if I count, I go up 1, 2, 3, and then over 1. 3 over 1 just gives me a slope of 3. So my first equation here, I'm just going to write down the 3x minus 4, comma, and then I want to write between what 2 domain values this occurs. So I'm looking at x. All right, so my first value here, let's see if you can see my tiny little cursor there. My first point is at -2, -10. So what is the x value here? I hit at -2. And then it exists over here until I get to 1. So this piece of the red part of the function exists between x is -2 and 1. So -2 and 1. And then I have to pick the appropriate signs. Because my first dot is closed, that's going to mean less than or equal to. And my next dot is open, so that's going to be just less than. So if that's a helpful note to make, I'll make that note over here. If it's a closed circle, then I'm going to have either less than or equal to or greater than or equal to. If I have an open circle, then that's either going to be less than or greater than. All right, so I've got the red part of the function. Now we go to the blue part of the function. Now for the blue part of the function, I still need the y-intercept. And it doesn't cross the y-axis, but I can imagine that if I extended it, it would cross right here at 3. So I've got a y-intercept of positive 3. And when it's really close to the y-axis but doesn't cross it, it's really easy to use this. We'll see on a different problem later on how sometimes we have to use another method to find that y-intercept. But when it's pretty obvious from the graph, I can go ahead and extend that just a little bit. So then my slope, to get between any 2 points, I go up 1 and then over 1. So this has a slope of 1. All right, next part of the graph. Instead of writing 1x, I'm just going to write x plus 3. And then I want to know what are the x values where that exists. So let's see, if I follow this first point down, right, it starts at 1. And the last point is here at 5. Now, both of those are solid blue dots. So the x values are from 1 to 5, including 1 and 5. So 1 is less than or equal to x is less than or equal to 5. Now, in order for something to be a function, right, this is a piecewise function, that means that it has to pass the vertical line test. So for every value of x, there's only one y. Which means that in this point here, if that is solid blue, then that means that it's going to be an open green circle, because it can't be both. So I work to write the equation for the green part. And let's see, I can extend this, and that's going to hit right here at 8. And the slope of a horizontal line, I go up 0 and over. Well, up 0 and over just actually is a slope of 0. And the equation of this graph is just y equals x, or f of x equals x. I'm sorry, y equals 8, or f of x equals 8. Over what x values does that piece exist? Well, it starts at 5 and goes to 8. In this case, because I already included 5 into the blue function, this is going to be just less than instead of less than or equal to. So it's going to be between 5 and 8. And this whole part on the bottom here, that is my answer. This entire function. Okay, we're going to do it again for problem B. Now in problem B, I purposely did not color coordinate them because we're going to have to make some choices. So I'll zoom in, and you want to pause this video and copy that down. So I'm still going to color coordinate these while I write the answers, but they're not color coordinated on here because we're going to have to make some tough decisions. So I'm going to call this function, part of the line function A, this part of the line function B, and this part of the line function C. This makes it a little easier for you to determine what I'm working on. All right, first equation of the line. I have this horizontal line here that I labeled A. Now we just did a horizontal line. Horizontal line is going to be y equals some number. And this crosses at y equals 7. Has a slope of 0. So when I plug in a slope of 0 and a y-intercept of 7, I just get the equation f of x equals 7, or y equals 7. Now I have to find the domain where that part of the graph exists. So I look only at the x values. Imagine that I'm smashing this function down on the x-axis. So I hit here at -5, and I hit here at -2. So I've got a solid dot at -5. That's going to be less than or equal to. And at -2, I have a choice to make. And I'm going to come back to talk about this. I'm going to just leave it as less than for now. Because I can either include this point right here with A, or I can include it with B, but not both. So you can make a choice. Okay. Writing the equation of the line for what I labeled B, my second part here. My y-intercept is up here at 3. It's a positive 3, not a -3. And I got to calculate the slope. So between any 2 points, I go down to right 1. And a slope down to right 1 gives me a slope of -2. The equation of the line is -2x plus 3. What x values does that exist on? Well, from -2, and the last one is over here at 3. Now 3 is absolutely a solid dot, so that's going to be or equal to. Here's where I have a choice. There is no way for me to know with certainty if, here I'm going to highlight it, this point here belongs with the piece of A function or the piece of B function. So I get to pick, which means that I can either include it with the red function and do or equals to down here, or I'm going to erase and do it again, or I can include it here. And one is not more correct than the other, so you get to choose. I can't do both because it can't exist in both spots because that would make it not a function. So you might want to rewind that 15 seconds and listen to it again. You have a choice whether the or equal to goes here or here, and you can't put it in both. You have to put it in one. All right. We're going to write the equation of the C part of the function, and this one's going to be a little bit more complicated because I can't just extend it really quickly to see where that intersects the y-axis. So we have to use a new, or an old strategy actually. But something we haven't done in a while. All right, so I can't readily tell where B is, but I can find the slope, so let's do that. So this goes up 1, 2, 3, 4, and right 1. So I get 4x and plus b. But I can't tell where b is, and even if you try to extend this, I mean, you might get close, but you might not hit the right number. So what I'm going to do here is I'm going to plug in some other point to find b. Plug in a point on the line to find b. So I can use some other point. I like the point, let's see. How about this point right here, which is 5, 9? Great. So I'm going to plug 5 in for x and 9 in for y, or for f of x, and do a little math. So I'm going to replace f of x with 9. X is 5. And now I only have one variable. So I can substitute in, evaluate, find b, and then plug that back in at the end. 4 times 5 is 20. Subtract 20. And I get negative 11 is equal to b. Great. Now I can finish writing the equation of that line. And I get 4x minus 11. And we need to determine what x values that occurs between. So the first value that it starts at is 4. And then it ends at 6. So between 4 and 6, I have a solid or a closed circle at 6, so that is going to be or equal to, and I have an open circle at 4, so I'll just leave it like that. All right. This problem also asked me to talk about domain and range. I'm not going to do it for A and B, but let's go through and we'll talk about it for A. So I'm going to go back to A. We've got a little bit more room up here. And let's talk about the domain and range. So the domain, what are all the possible x values for this function? Now, when I'm talking about the function, I'm talking about all of the pieces combined. Okay. So the very first, most left part of this graph, the first x value is going to be negative 2. And then it exists on the red until I get to 1. It doesn't exist on the red function at 1, but it does exist on the blue function at 1, so it's still continuous. Then on the blue function, it exists at 2 and 3 and 4 and 5, and then it jumps to the green function and exists all the way until you get to 8. So I've got from negative 2 to 8, and I need to pick whether I have square brackets or round parentheses. Because the point at x equals negative 2 is closed, that's going to be a square bracket. It means it includes negative 2. And because the number where x is 8 is an open circle, it's going to be a parenthesis. All right, let's talk range. Now, when I look at the range, when I look at the y values, I have a gap. So it goes all the way down to negative 10. It comes up, comes up, comes up until I get to negative 1. And then there's a gap. So let's write the first part first. So it's negative 10 all the way to 1. And 1 is an open circle, so it's a parenthesis. Now we can write this as a union. Sometimes on the Pearson homework, they ask you to just use a comma, so be aware of that. If you write it with a union symbol and it says, that's not right, write it like this. Just be aware that they might be looking for a comma in between your two ranges. The next y value as I go up is 4, and that goes all the way to 8. Now, I have an open circle and a closed circle at 8, so I'm going to include it because it does exist at 8. So then I have from 4 to 8. We talked about domain and range a lot in 1.1, so I'm going to skip example B doing domain and range. And we will talk about it on the next example because it is a unique scenario. For example 3, now we're going to make our own graph given the function. So go ahead and write down that entire function and make a spot on your paper for this graph. Okay. Again, I'm going to color coordinate these. So makes it a little easier when explaining and trying to get people to follow. I'm going to graph these 3 equations. When graphing, you might want to do this in light pencil so you can erase it if you go past the domain, which is totally great. I'll be using my erasing function on some of these. So the function is, the first one, 1/2 x plus 3. It only exists between x is negative 2 and 0. So I'm going to graph the function first and then worry about the domain. So y-intercept of 3. Got it. And my slope is up 1 over 4. Up 1 over 4. And I'm also going to go the other direction. I would recommend if you have a straight edge to use one. All right. Okay. Now this part of the graph only exists from negative 2 to 0. So I'm going to erase the rest. I know I just drew all that. But I'm going to erase it. So I don't want it to go past 0. And I don't want it to go beyond negative 2. At negative 2, I need an open circle. And at 0, I need a closed circle. So there's my first piece. All right, the blue piece, y equals 2. So y equals 2 is a line that's horizontal. At 2. But here, this only exists from 0 to 4. So I'm going to erase everything that falls outside of those boundaries. Now at 0, I have an open circle, and at 4, I have a closed circle. And the third part of my line is negative x plus 3. So we have a y-intercept of 3. And then the negative x means that this has a slope of negative 1 over 1. So I go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, like this. This part of the domain is a little bit different. It just says when x is greater than 4. So it's actually going to start at 4. Greater than just means it's going to keep going forever and ever. It's actually not going to stop. So I'm going to make sure it goes to the ends of my window. It's going to be an open circle at 4 because it's not included. So there's my graph. Done. Beautiful. Now let's talk about domain and range. So some unique things happen here. When I look at domain, right, the x values, if I take this, I smash it on the x-axis. So this comes down, right? So I hit negative 2. That's good. When I go at 0, the graph is a solid circle here, but an open circle here. So it fills in. Just imagine one on top of the other. It fills in. It exists at 1. It exists 2, 3. At 4, it exists up here, but not down here. That's okay. It exists at 5 and 6 and 7 and 8. And it's going to keep going and going and going and going. I could keep plugging in numbers. So it starts at negative 2. And this is going to go on forever and ever and ever. We call that infinity. I can never include infinity, so it's always a round parenthesis. And negative 2 is not included also, so it's going to be a round parenthesis. All right, now let's look at the range. When I look at the smallest value of the range, I go down, right? This exists below negative 1, negative 2, negative 3, negative 4, negative 5. This is just going to keep going down. So it's going to exist at negative infinity up until I get to negative 1, and then there's a gap. Now I'm going to use the union symbol, but remember on your Savas-Pearson assignment, it might just ask for a comma. Now there's a gap from negative 1 until I get up to 2. The graph exists at 2, but then it doesn't, then there's another gap until you get up here. And this number right here is actually 2.5. I know that because it's a slope of 1/4 and it hit this point when I graphed it originally. So I hit the number 2, but that's not a range of values. It's just 2. So when I want to say that just one number and not a range of numbers is part of the range, I'm going to use these different parentheses to mean just 2 and another piece. The rest of the range, remember, I'm smashing this now on the y-axis, goes from 2.5 to 3. 2.5 is going to be an open circle, and then 3 is going to be a closed circle. So this may be a different way than you've ever written a range before, so check it out, review it. It's a little bit more complicated. All right. Now, this isn't already plugged in here, but a reminder, in case you forgot from Math 1 and Math 2, how do I evaluate a piece of a function or a piecewise function at some number? So let's talk about this. So when given an opportunity to evaluate the function at some number, I have to evaluate where does the graph exist at For example, f of 4. So I have 4 here. Which one of these domains does 4 exist on? Does it exist between -2 and 0? No. Does it exist between 0 and 4, including 4? Yes. So I am going to evaluate at this function because that's where 4 fits. Well, the function is f of x equals 2. So f of 4 is just 2. Well, that didn't take much evaluating. Let's go for the next one. F of 6. Where does 6 exist? Well, it doesn't exist between -2 and 0. It doesn't exist between 0 and 4. But it does exist greater than 4. So that's the piece that I have to plug 6 into. So I get negative x plus 6, which turns into negative x plus 3, which turns into negative 6 plus 3, which gives me negative 3. If you need a little bit more instruction on that, you could always look up a video on evaluating piecewise functions at a value for x. Okay, so here we come to our last type of, the last one that we're going to look at in this class, which is writing the absolute value function as a piecewise function with linear parts. All right, cool. So when we were looking at absolute value functions previously this year, we were using this structure when we were working on graphing. So y is equal to a times the absolute value of mx plus b and absolute value plus c. Now, we're not exactly talking about transformations here. We are talking about graphing this and looking at the graph and then rewriting that as a piecewise function. So if you remember back to graphing and kind of looking at what this graph is going to look like, the first part that I would work on when determining is, one, what type of function is this? Absolute value, so it's going to be a v. Now, because it's positive in the front, I know that that v will open up. And this problem does not ask me to graph, so I'm going to sketch it to help me write the piecewise function, but it's not going to be super precise. Okay. All right. So to start off, I'm going to take what is inside the absolute value and I'm going to set that equal to 0. So I have 3x minus 12 is equal to 0. And then solve for x. So I add 12 to both sides. I get 3x is equal to 12. Divide both sides by 3, and I get x equal to 4. When we were graphing this previously, we would take what is inside the absolute value, set it equal to 0 to get the x-coordinate of the vertex. And then to get the y-coordinate, you can either take 4 and plug it back in, or you can remember that whatever is added or subtracted outside the absolute value is going to be the y value of my vertex, right? So this c is always the y value of the vertex. I don't have anything here. I'm adding or subtracting 0. So my vertex is 4, 0. If wrapping your head around that is just too much, then know that anytime I have an x value, I can just plug that x value in to find y. So I could also do it this way, right? Where this is the absolute value of 12 minus 12, which is just 0. So either way. Okay, so if I look at a sketch here, again, not going to be real precise, just looking at an about. I have a vertex of 4, 0. I know it opens up. And we can talk about slope also here. So back when we were reviewing graphing absolute value, we talked about how the slope is equal to a times m. And in this instance, the a, which is the number in front of the absolute value, is just 1, and m is 3, so I have a slope of 3. That means this graph is going to be narrower. Pardon the bell. The equation y equals 3x minus 12 belongs to 1/2 of this graph. All right, let's think about it. With a y-intercept of negative 12 and a positive slope of 3, that's talking about this portion of the graph. This other portion is just going to be the opposite. So this one that I just highlighted in purple is going to be the opposite. One of them is going to be what's given, and one of them is going to be the opposite. So take the opposite to get the other equation. So I want the opposite of 3x minus 12. And when I distribute that negative 3, it gives me negative 3x plus 12. So here are my two equations. I have 3x minus 12, and I have negative 3x plus 12. And I still have to talk about what domain do those exist on. Okay, this point here is 4, 0. The x value is 4. So this pink part of the graph, or this reddish part, exists when x is greater than 4, right? It exists all of these numbers over here. So this is going to be x is greater than the x value of 4. And this purple part, the opposite part, is going to exist when x is less than 4. Now, one of these needs to be equal to. It doesn't matter which one you pick. I could pick 4 is greater than or equal to 4, and you could put it on the x is less than or equal to 4, and we could both be right. But you have to pick one. You can't pick both. So we wrote our own piecewise function from the absolute value function. We're going to do it again. The process is the exact same. If you feel comfortable, you might want to pause this and try this problem on your own. We learn most by learning what we don't know. All right. So I want to start off with coming up with some kind of a sketch of what this looks like to help me write the piecewise function. I'm going to do that by finding my vertex. So I set what's inside the absolute value equal to 0 and solve for x. My vertex is going to be negative 2.5 comma 0. Because again, I have nothing added or subtracted to outside the absolute value to change my my vertical shift, to change my y value. So when I go to sketch this, let's see, negative 2.5, 0. This opens up again. Let's look at the slope. The slope is going to be 1 times 2, so I have a slope of 2. So again, it's going to open up and it's going to be a little steep. Just to get an about. Okay. I know one of the equations is 2x plus 5. So just drop the absolute value of the original function. Which one is that, though? Let's see, this is a positive slope with an intercept of 5. Okay. So is it the part of the equation on the right side of this or on the left side of this? A positive slope is going to be this side. So I've got 2x plus 5. Almost given to me. But then where does that domain exist? Well, the x value is negative 2.5, and I'm talking about the numbers greater than. So this is going to be x is greater than negative 2.5. So what's the equation of the other part of the graph? This part over here is going to be the opposite. So I'm going to take the opposite of 2x plus 5, which gives me negative 2x minus 5. Where does that exist? That exists at all the numbers less than negative 2.5. One of these needs to include the vertex. So this time I'm going to put it on the bottom one. It doesn't matter as long as you include it once. And there's my piecewise function for the absolute value described in B. All right, thank you. I hope this helps give you an idea of piecewise functions.